in order to figure out what the image of this map is, you just need to look at every curl in the manifold and look at the thing at the north pole and the south pole, look at the difference and make sure it's divisible by something. Okay, so this becomes quickly some very combinatorial or algebraic, commutative algebraic calculation. And so examples, if we're in the case of applied variety things, polynomials will look like this. And for Grassmannian, we already have something like this. And there have been a lot of people who have used this to say some things. And of course, you can't read that, but I'll tell you a little bit about one of these papers. Okay, so this paper that I worked on as a postdoc talks about generalizing this result to, say, spaces even like loop spaces in a Lie group. So the GKM description works, even in infinite dimensional cases. It works for equivariant cohomology that we already knew. Sometimes works over Z if you're a little more careful. It works in K-theory, and here I mean topological K-theory. In some cases, this agrees with operational K-theory, if you're looking at the algebraic type, which agrees with algebraic K-theory for nice classes. And this equivariant K-theory description, say, for loop spaces, was known already by Kaufman and Kumar in the 80s. And then it's also known in equivariant cobordism. And of course, these examples are only really, I mean, these computations are only really useful if you know what the equivariant theory of a point is. And here we do, and here we do, here we don't. I mean, well, we do, but we can't really compute. So it's, I mean, this is a theoretical theorem that's what is true is that we understand Euler classes, and that's what you need to understand really the image. But it's maybe of questionable use. But okay, I shouldn't denigrate my theorems, I guess. So, okay, in any case, this has sort of further applications and further thoughts. In Schubert calculus, this has been used by various people to to think about different ways of doing Schubert calculus. I had hopes that this would lead to sort of easier combinatorics, but as far as I know, it hasn't yet. And it does, I mean, in theory, these are all just commutative algebra questions now, so you want to just program them in Macaulay 2 or something like that. But Macaulay 2 really likes closure rings and really hates subrings, so it's very annoying. And if anybody has advice about how to ask questions about subrings, I would love to know. You can do some calculations of Roman Witten invariance and quantum corrections. You have to be careful what you mean by quantum corrections or what you mean by equivariant quantum, blah, blah, blah. But there are possible ways to do this, and I'll say a little bit about this towards the end. And this has also come up in work of Masuda, Panov, Puck, when they were studying something called porous manifolds. This is now in a very topological category so far. Almost everything could be a projective variety, and so it's not saying very much, but theorems like this are true in a more topological context. And actually, one of the things I'm working on this semester with Henri Piroche is studying toric origami manifolds. What those are, they're a class of something called folded symplectic manifolds. And folded symplectic manifolds, it's another geometry defined by a differential form, and in that case, the differential form, the existence of the differential form is equivalent to existence of stable complex structures. So again, this gets into sort of very topological direction, the kinds of questions you ask. There is, in certain cases, we have some sort of GKM theorem, but in other cases, the fundamental group isn't zero, the spaces aren't simply connected. The fundamental group is not like the fundamental group of an algebraic variety, so algebraic varieties, I guess, have to have fundamental groups with even rank, and that's not true here. You can have S1 plus S3, and so you have fundamental group Z. And the big question, of course, maybe is topologically, can you determine the manifold combinatorially with some, combinatorics up to cobordism? Okay. I am apparently talking very fast because usually I don't get to this point about half an hour in. Okay, so any questions? Okay. So in the last part of the talk, I wanted to say something about symplectic reduction and how these localization techniques can be used to say something about symplectic reduction. So symplectic reduction is the way of constructing quotients, constructing new examples from old ones in symplectic geometry. We have this momentum map, and in the symplectic category, you can use this to prove a lot of the results that I talked about already. And essentially, the reason is that this peak C, these individual functions behave like Morse functions. They're Morse functions in the sense of Bott, which just means that they maybe don't have isolated critical points, but they're good enough. Oh, right, and I was supposed to mention, I mean, of course, it's celebrated, right? So Morse was here and developed Morse theory here, except that I was at Cornell recently, and my chair reminded me that, in fact, Morse was at Cornell before he was here, and the very beginnings of his of Morse theory were developed there, but okay. Okay, so the reason this momentum map is useful is that you can do Morse theory. It's also an equivariant map, and so that means that this level set, phi inverse of mu, any level set, is a T invariant submanifold. And if mu is a regular value, this is just differential topology. The level set is a submanifold. Okay, so you might say, well, it's not a symplectic submanifold of our original manifold, and of course, no, it's by differential topology. The level set is dimension m minus dimension t, and we know manifolds, symplectic manifolds are supposed to be even dimensional. But the miracle that happens is that I can restrict the 2 form to the submanifold, and the directions where it's degenerate are exactly the orbit directions for this t action. And so this, if I quotient out, this thing is even dimensional, and the theorem is that this quotient phi inverse of mu mod t is a symplectic space, and it has at worst orbifold singularities. Okay, so this is the way to construct new examples. The basic example is this. Look at the circle acting on Cn by just scaling each coordinate, so that's my action. My momentum map for this action just takes a string of n complex numbers to the sum of the lengths. The level set at mu, this is just going to be a 2n minus 1 sphere, and the circle acts on this, and the circle direction, that's just a hot vibration. So the quotient is just Cpn minus 1. Okay, so that's a very explicit way to see Cp n-1 is symplectic. And Dalton's theorem says that compact toric symplectic manifolds are in one-to-one correspondence with some adjectives applied to convex polytopes. And the way he proves the existence part of his theorem, given a polytope, there is a symplectic manifold, is he says, well, okay, given a polytope, here's a way to take an affine space, where n is the number of facets in the polytope, divided by a torus that is of the appropriate dimension, to get a symplectic manifold. It has a residual, so let's see, Tn really acts here, and so there's a residual Tn minus d action on this, and this is the moment polytope for that residual action. Okay, and the combinatorial torus all works out very nicely. I should say the GKM theorem applies here. The condition that all of these checking for each edge, all of these divisibility conditions, is equivalent to checking that an assignment of polynomials on a fan is a global piecewise polynomial. So there's been a lot of combinatorial work done on the ring of piecewise polynomials on a fan, and that's in some way just a reinterpretation of the GKM theorem. And so we can one might hope to understand that combinatoric a little better. Some more examples of quotients. If I have, let's see, so I have a Tn action on a flag variety, on Grassmannians, on cojoint orbits, homogeneous spaces in general. These quotients are called weight varieties because depending on the symplectic form that you choose on these, and depending on the regular value where you reduce, this tells you something about weights of the torus action of a G action on a so if you think of a G rep, how do you break it up as a T rep in terms of your reducible representations? And so these are called weight varieties because there's there's a deep connection between these quotients and the corresponding representation theory. Okay, so another example, I said that we would see this as symplectic. It's symplectic because, well, we have this description. We have n vectors in R3. They're supposed to have length AI, so that says that we're living in a product of two spheres. This adding up to 0, it turns out, is just a momentum map condition. That's taking a level set at 0, and then we're dividing out by SO3. And so this is a symplectic quotient, and it fits nicely into the Gelfand-McPherson correspondence, where so we can think of this product of S2s as a quotient of C2 to the n, and I quotient by torus, and then by SO3, I can alternatively quotient by U2 and hit the Grassmannian on the other way around at the diamond, and think of polygons as a quotient of a Grassmannian. So depending on how you want to think about your polygons, or depending on the kind of geometric calculation you want to do, torus quotients are sometimes easier, and this space we understand pretty well, like this space. So, okay, so cohomology of symplectic productions. Francis Cohen showed in the 80s that if we have a compact Hamiltonian T-space, then, so we know that the inclusion of